So, hi everyone. It's Chérif Matta here from Mount Saint Vincent University, your host for the program of Conversation with a Scientist. And today we don't only have one scientist, but we have two great scientists. One is at an advanced career stage, and the other one is at the initial career stage, early career stage. So it is my great pleasure today to interview Professor Tina Harriott, colleague here at Mount Saint Vincent University, and also to interview a very promising early career scientist and colleague, Ailish Sullivan. I pronounce it correctly, Ailish or Eilish?
Yes, Ailish.
It's Ailish.
You do it right, yeah.
Okay, Ailish Sullivan, who is a former honors bachelor degree student of Professor Tina Harriott, and they both work on the story that we will tell you about tonight, which is called the Diffuse Interstellar Bands. And from the name, it sounds very exciting for some, very mysterious for others. So it has to do with diffused. Something is diffuse. It has to do with space between stars, interstellar space, and then band. And that is not a rock band. It could be something else, probably. So we'll see what that is, the story of today. So let me say a couple of quick remarks about our guests today. Dr. Tina Harriott is a gravitational scientist. Her main interest is the general theory, Einstein's general theory of relativity. She holds a BA in mathematics from the University of Cambridge, a master's in astronomy from Sussex University, and a doctorate from Dalhousie University here in Halifax. Ailish has just graduated with a first-class honors in chemistry from Mount Saint Vincent University, where we are here today, the studio of the university. She received the President Medal upon graduation. She received twice an undergraduate student research award from NSERC. And for those who are not in Canada, NSERC is the Natural Science and Engineering Council of Canada. She also received the Jean Sauvé Award for Women in Science. She has won several, not one, not two, but several best oral presentations in national and international conferences. And she has published a scientific paper, and more to come. Shall I say more? But anyway, I'll stop here. And I will turn the mic to our two guests and wonder if there is anything that you would like to say about yourselves that I missed here. So maybe Tina.
You covered the main points, but maybe I'll just say that I've always had a love of math, physics, and astronomy, and I feel very fortunate to have found this research project with Ailish and others that kind of combines all of those things together.
Ailish?
Yeah, again, you did cover most of the basics for me, but I guess I could add how I found myself in the group, not being a faculty at the school, but I got involved after my second year of university, where luckily Dr. Matta, you, and Dr. Harriott took me under their wing to join this team, and I've been working there. I'm officially graduated, but I still like to keep involved with what's going on with the group.
Thank you very much. By the way, what does Ailish mean? You're the only Ailish I've ever met in my life. So.
There's a Gaelic Ailish and an Irish Ailish. There's different spellings, and it means Elizabeth.
Oh, okay. Yep. All right. Thank you. So we should probably, because the topic is rather specialized, or the story, I like to call it the story of today's program, is rather a specialized one. So we should briefly start by setting the ground even for the audience. And hence, before we start, let's talk about basics. Like, for example, what is an electromagnetic spectrum? So if you might like to start, Ailish or Tina?
Yeah, I'm going to let Ailish start us off.
The electromagnetic spectrum essentially is how we classify electromagnetic radiation. So it's just a simplified breakdown where we can categorize it. And there's lots of different types. Everybody watching is definitely familiar with at least the visible light region, as that is the light that we can see with our eyes. But there's a few other categories, and if you can look at image of the electromagnetic spectrum, you'll see that the frequency of the radiation changes depending on which category you're under.
So why are spectra useful for astronomers and other scientists? So it's the question for Ailish and Tina.
Okay, I guess I will grab that. First of all, let me just say that the rainbow spectrum that everyone is familiar with, that Ailish mentioned, is just one type of spectrum. And if instead of just looking at the spectrum formed by general white light, you look at a spectrum formed by a single atom. And here I've got 4 examples of 4 different gases. You will see that these spectra look quite different. They're called emission spectra because you can see that there are a series of bright lines. Now, the most important takeaway from this is when you look at those lines for the different elements, you can see that none of them are in exactly the same place. And this means that these lines act like a fingerprint. And this is incredibly valuable for astronomers because, of course, we cannot touch our material that we're studying. And so this is the only way we have, really, of knowing what elements are found in stars and galaxies is to look at the spectra that we receive. And by identifying those bright lines, we can identify the elements that are found.
So we know the composition, the elemental composition of the star by analyzing the light through spectrophotometers here on Earth, and then we get these spectra, and from these spectra, we can work our way back and determine the type of elements and their relative abundance in the star material.
The abundance is a trickier question because it depends on the temperature as to whether the lines are present, but essentially that's absolutely correct.
Okay.
Now, there's one other little complication to mention is that this is the type of spectra you find in the lab if you heated up a gas and then looked at the light emitted. But that's not actually what we see most of the time in astronomy. So if we look at this next picture, you will see that I've got at the top the rainbow spectrum we've talked about, and in the middle is the emission spectrum, which is what you get from a hot gas in the lab. But there's a third type of spectrum called an absorption spectrum, and this occurs when you have a hot gas that is sitting behind a cool gas in the direction that you're viewing. Now, again, the details are not important, but the main takeaway to remember here is that if you look at the position of the bright line and then the dark line for hydrogen, you will see they are in exactly the same position. So if you see an absorption spectrum, you have the same valuable tool to determine what the element is inside of whatever it is you're looking at. So why do we see an absorption spectrum in stars? Because that is the main type of spectrum that we see. And the answer is that the continuous spectrum, the one at the top, is formed in the star's interior, which tend to be millions of degrees in temperature. It's a hot, dense mixture of gases, and so it produces the rainbow spectrum. But between the interior and us is the atmosphere of the star, sometimes called the surface of the star, but that's a misnomer because, of course, there's no solid surface. But the atmosphere is a few thousand, maybe a few tens of thousands of degrees. And so when we look at a star through our telescope or spectrograph, we're seeing the cooler atmosphere in front of the hot interior. And as a result, the typical spectrum seen from a star is an absorption spectrum.
So is there any other aspects of physics that we need to know before delving into the story of today, the DIB, the Diffuse Interstellar Bands?
There is indeed one other important thing that we need to discuss, and I'm going to let Ailish tell you about that.
All right, so the other topic that we should cover is what exactly the Doppler effect is, as it is relevant to DIBs. So we talked a little bit about the electromagnetic spectrum and how we observe electromagnetic radiation. And the Doppler effect is essentially an effect that can happen which changes the way that we observe it. And it all boils down to essentially where our position is relative to an object that may be moving. The simplest way to describe this is if you think of sirens that you may hear on a vehicle traveling through the city.
Emergency vehicle.
Of an emergency vehicle, of course. So you might see them drive past you, and as they're approaching you, the frequency of the sound is really high, and then you notice as it passes you, all of a sudden the frequency becomes lower, and this is essentially you experiencing the Doppler effect in action. Exactly.
Right?
So the frequency of an object will appear higher as it's traveling towards you, and then it appears lower as it's traveling away from you. And this also applies to stars or any astronomical spectra which we're observing when our relative motion is changing. So it's known as either red shifting or blue shifting. So as it is traveling away from you, you'll experience that red shift and the blue shift while it's traveling towards you. And this is the same that occurs with a star, so when you're observing its spectra. So as it is traveling away from you, you'll experience that red shift and the blue shift while it's traveling towards you.
And it's called the Doppler effect.
And that's known as the Doppler effect.
So just maybe before I put the movie up, I'm going to say one other thing, and that is what we are looking at are what's called binary stars, which are two stars, and they orbit around their common center of mass, as seen by us on the Earth. And so, as Ailish described, we're going to see the Doppler effect when we receive the light from these stars, because they're either moving towards or away from us. Okay. So if we look at the movie, we can see that there's one star that's moving in a fairly large orbit and another star moving in a smaller orbit. We're going to assume, for the purposes of this example, that we can see only the spectrum from one star. We'll imagine the star that's moving in the larger orbit. And if you look at the bottom of the movie, you'll see that there's a spectrum, and we should all know now that this is an absorption spectrum because it's a continuous rainbow crossed by dark lines. And you can see that as the star moves towards us, the lines shift one direction, and then as it starts to move away, they shift in the other direction. So we have this periodic back and forth of the absorption lines in the star. Now that's nothing new, really. It just confirms everything that we've talked about. However, if you look closely at the spectrum, you'll see that there are 3 magenta lines there. And look very, very closely, and you'll see that while the absorption lines in black are moving back and forth, the magenta lines are staying stationary. Those magenta lines are what we call DIBs.
Why are they stationary?
Well, that is an excellent question. When it was discovered that there were these stationary lines, immediately astronomers realized that these lines could not be formed in the star itself. Otherwise, they would be moving. And it was hypothesized that these lines are formed in the space between the stars that is not actually empty, but that space is filled with gas and dust clouds.
So it's between us and the star.
Yeah.
The double star, let's say, that are
right.
emitting the light that is being absorbed by the dust in between.
Yes, the dust and gas, and of course the reason why we're studying this is that nobody knows exactly what the molecules are that are causing these lines. They're not simple atoms because we would have been able to determine what they are. But
Okay, that part explains why they're called interstellar. Now, how about diffuse part? Why are they called diffuse? And maybe
I'm going to let Ailish answer that a little bit.
Yeah, so essentially they're known as diffuse interstellar bands because the absorptions that we are observing are often more broad than what's typically observed in astronomical spectra.
I will just say one last thing, of course. Those lines in reality that I have in magenta to stand out, they would just be dark absorption lines like the others.
Yeah, and who discovered these lines and when?
My esteemed colleague is going to answer that.
The first diffuse interstellar bands were observed by Mary Lee Hager, who is an American astronomer who was studying at the Lick Observatory. I believe they were discovered in 1919.
1919.
1919, yeah, so around a century ago.
Okay, and that brings a point that we are very passionate about in this university here, Mount Saint Vincent University, and that is the role of women in science, which was historically less emphasized and perhaps even ignored. And of course, there are many women that have contributed considerably to the development of modern science. We can name a few here just for illustrative purposes, but there are many more, of course. Marie Curie, Emmy Noether, Mary Lee Hager that you just mentioned, Mount Menton, who is a Canadian biochemist of great importance, Ada Yonath, these are more modern scientist, Ada Yonath, who won a Nobel Prize in 2009 in chemistry. Donna Strickland, again a Canadian, who won the Physics Nobel Prize in 2018, just to name a few. So I think you have nice pictures here of some of these people. So
I do indeed. And perhaps before I move on, I would say that you're correct. These women are all remarkable scientists, and yet at the time, they all struggled for recognition, essentially throughout their careers. And Emmy Noether is now regarded as a remarkable mathematician. She made contributions in a number of areas, from abstract algebra to mathematical physics. And just as an example of the type of problems they ran into is that when she finally got a position at the university after being invited by another famous mathematician, Hilbert, she was not allowed to lecture for 4 years under her own name. The lectures were advertised in Hilbert's name, and she was listed as an assistant. I mean, she eventually gained respect and recognition, but it was a struggle. There
is even a prize in mathematics named after Noether these days, right?
Right,
yeah.
right. Yes, indeed. So I think we certainly have it better than these women did, and I think thanks in part to the tireless efforts of individuals and institutions to try and change the culture. And we are very fortunate to be here at Mount Saint Vincent, where one of their primary goals is to increase the diversity of faculty and students. And there are many initiatives dedicated to try and encourage women into the STEM fields. There's prizes and things like that.
STEM, just for the audience that is perhaps not familiar, is science, technology, engineering, and mathematics. Right. It's abbreviated as STEM. It's a well-known abbreviation in academic circles, but I'm not sure if it is well-known outside, so I just wanted to clarify that.
So, and the Mount often recognizes the achievements of women and things like their convocation by giving them honorary degrees. And here are two examples. I'm sure everyone is familiar with Hillary Clinton, former U.S. Secretary of State.
She got an honorary degree from the Mount, from Mount Saint Vincent University here,
yes,
from this university.
1995, I believe.
And this is her in our convocation here, right?
That's right, yes. And Ada Yonath, who I believe you know very well, Nobel Prize in Chemistry, also an honorary degree recipient from
Mount Saint Vincent University.
That's right. And so, as I say, I think that things are changing. I'm not saying there's no work to be done, but women are now recognized often at the time for their achievements. And an example is another lady that you mentioned earlier, Donna Strickland, who is a Canadian physicist, Nobel Prize winner for her work on making laser, high energy, short duration laser pulses, which have a variety of uses.
Being yourself as women, do you think there are still barriers nowadays? Of course, the situation is far better than what these women have struggled with back then. But is the situation better now, and is there still work to be done to remove the systemic barriers against the advancement of women in STEM fields?
Okay, I'll just say a little bit more, and then I think Ailish probably has some good comments as well. If we turn back to astronomy, I have two examples. Jocelyn Bell struggled in her early career, I think, to gain the recognition for her remarkable work.
What was her work about?
She was one of the discoveries of pulsars, which are very dense stars that are emitting pulsed radiation that's picked up primarily by radio telescopes. However, in her later work, she was recognized. She now has numerous awards and honors, and she was named the first female president of the Royal Society for Scotland quite recently. And on the right is another astronomer who broke the so-called glass ceiling by becoming in 2021 the first astronomer royal for Scotland, who was a woman.
And what exactly is the astronomer royal for those who...
It's a largely ceremonial position now, but when it was created several hundred years ago by the King of England, it was to oversee some of the real problems of the day, like timekeeping.
Calendars.
That's right. That's right. And running the Royal Greenwich Observatory and things like that.
And you too, have you ever experienced such barriers, and how did you manage to overcome them?
I will let Ailish go first. Yeah, so while as Tina mentioned, there definitely is still work to be done, and there probably will still need to be some work done for a while, but at least in my own personal experiences, I have been very fortunate in having a very supportive and encouraging team behind me. My family, of course, has always encouraged me to pursue a career in science, and I have been accepted with welcoming arms when I got to Mount Saint Vincent to continue a career in science and practice in that field. And of course, we've already mentioned a few, but I have been lucky to receive some awards that have been dedicated for women in the field, of course.
Like the Jean Sauvé.
Jean Sauvé, and the Doug and Joy Harriott Award for Physics, of course, is another one. And I have been fortunate enough to participate in lots of events, of course, too, such as the Canadian Conference for Undergraduate Women in Physics, which, of course, all these efforts are definitely helping to advance the
And I
field.
think you got an award there as well.
I did get an honorable mention, yes, for my talk at that conference. Yeah.
Well done, Ailish. Really congratulations for all the great work you've done and
Thank
you're
you.
doing.
Yes, well deserved.
Pardon me?
It was well deserved.
Yes, absolutely. So I'm going to go back to the DIB problem, the diffuse interstellar bands. Why is it important? Is it a mere curiosity, let's say, or is it going to help us understand better aspects of the functioning of our universe or its origin, or perhaps even can it illuminate the origins of life, perhaps even intelligent life in the universe, or what? Why are we studying diffuse interstellar band? And this question is for both of you, whoever wishes to start. Tina, maybe, or Ailish. Fine.
Yes, I guess I would say maybe a little bit of both. I mean, I'm definitely interested in what we're doing, and I think we're all always interested in what we're finding out, but there is some real application and some insight that we can gain because, of course, we are investigating the molecules that exist in space in the interstellar medium, which then does give us insight to the composition of those areas. And then, of course, you can tie that back to links of potential early life and that sort of stuff. So it definitely is very relevant work.
Yeah. I think human beings have always been curious, and what more fundamental question is there than how did life begin on Earth? And as Ailish says, by studying diffuse interstellar bands, we hope to learn what molecules exist in those gas and dust clouds. And those gas and dust clouds will eventually become the next generation of stars and planets. And so an understanding of what molecules form, how stable they are, I think gives clues to how perhaps life began on Earth and maybe elsewhere.
Yeah, so you're kind of looking at the history of the formation of new stars and planets by looking at the dust in between at the moment.
Absolutely.
Because it's an early stage of the formation of systems such as the solar system, let's say.
Right.
Right. Okay, and what is the current status of the research that you have been involved in and what is the problem that you're trying to solve in this general area of the diffuse interstellar band? If perhaps Tina can start on that.
Okay, sure. So, as we mentioned, they were first discovered just over 100 years ago, and now there are almost 600 different diffuse interstellar bands known.
In the visible part of the spectrum.
In the visible part of the spectrum mainly. And yet, despite this 100 years of research, and currently, as we speak here, there are many, many groups of researchers tackling the problem in many different ways. And Ailish is going to tell us about the method that we used in a moment. Yet, despite this, there are still no known, completely universally accepted sources for the DIBs. There is
when you say source, you mean the molecule that causes the absorption, or the molecule, or the ion, or the atom, or...
Right. Now, there are so many DIBs, and they are statistically uncorrelated. And so it's certain that there are many molecular carriers, not just one. So it's not like we're all looking for that one sort of answer. There are going to be numerous sources.
And what are we looking at here?
So what we're looking at here is, I said there's no known source, but in fact, it probably is not strictly true anymore. In the 1980s, Sir Harry Kroto discovered fullerenes, as I'm sure you know, and he immediately thought that they might be a candidate for a molecular carrier. Now, most people might be surprised because it's a very complicated molecule. It's a huge molecule, 60 carbon atoms, but in fact, it's very stable. So once it forms, he felt that it could be a source.
But here we're looking at its ion.
That's right,
positive
the
ion.
charged version, yeah. And in 1994, a husband and wife team suggested that two of the bright DIBs, you can see them there highlighted in the blue rectangle, which is close to the infrared region, so right on the edge of what we can see with our eyes. They felt that those two lines might be due to this C60 molecule. However, at the time, there was no laboratory spectrum for C60. And so the idea didn't really take hold until a group led by Maya in 2015 produced the spectrum of C60. And sure enough, those two lines were two of the lines produced
right on the spot.
Right.
Yeah.
And since then, there are three fainter DIBs that also match some of the other lines of the C60 plus molecule. And so there is now widespread acceptance for this as perhaps the first identified source for at least the DIBs on the edge of the visible region.
Right. And what new results your team has discovered in this domain, let's say?
Okay, since Ailish did most of the work, we're going to let her talk about this.
Yeah, so our research team so far has explored, as Tina already mentioned, there's around 600 DIBs that have been discovered so far in the optical range. And the first steps of the team was to sift through these DIBs and essentially find out which may be tied to each other. The database used, you can see the image here, was taken from the Apache Point Observatory catalog of optical DIBs. So
Where is this Apache telescope?
New
exactly where it is.
New Mexico? I see, right.
Yeah, so here's an image of the Apache Point Observatory where the DIBs that we use, the information at least was observed from.
You used the database that were produced by this observatory.
Exactly, yeah.
In what sense do you use what did you do with the database?
So we analyzed the DIBs that were in that database for correlations between essentially their intensity and their reddening to see which DIBs may be tied to each other.
And you wrote a computer software program that does this automatically, presumably because there are thousands and thousands of these possible pairs to compare, right? Because if you have like 500, you take 500 times 500, right? So it's an enormous amount.
Exactly, yes. So there was two other students that were working at the Mount at the time, and they worked towards a program to do those calculations to see which DIBs were related to each other. Emily and Fraser Smith were the students. But yeah, definitely through computer programming, that would have been a very challenging task to do by hand. I'm sure that we can all see how that could be a lot of work, not that it wasn't already by computer programming also. Yeah, so essentially we investigated to see which DIBs could be connected to each other. So as Tina mentioned, there's likely a lot of chemical sources for DIBs as there's so many, but potentially a few DIBs coming from each chemical source. So as she mentioned, carbon-60, there was 3 to 5 lines potentially associated with that molecule.
Yeah.
So, as mentioned, some former students did identify some DIBs through computer programming to see which ones may be related to each other. And of those DIBs, we call families emerged, essentially. And if you look here on the screen, we have one of the families presented, which is potentially tied to the DIB 5780 angstrom, which in fact was one of the first DIBs discovered by Mary Lee Hager at the Lick Observatory. So here you can see, if you look at the graphs on the right, the top graph shows a spread of all diffuse interstellar bands that are located in the catalog database from the Apache Point Observatory. And the bottom graph highlights which ones are potentially tied to the DIB 5780. And if we change the slide, there's a very similar graph shown for another DIB, 5797, which is the other that was discovered by Mary Lee Hager. And
the one that are in red are the one listed here. The
ones listed there on the left of the screen,
Right.
yeah. So those are the ones that are potentially tied to the DIB 5797. So from those families, this is where essentially I came into the research. The potentially associated DIBs were then compared to databases known as RASCAL, which stands for Rapid Approximate Spectral Calculations for All, which was developed by Clara Sousa Silva.
Whom you visited last year or 2 years ago.
So last summer I did travel to New York to visit her at Bard College so we could talk a little bit about DIBs and the RASCAL database itself. Yeah. So essentially, in the RASCAL database, it's approximated spectra and it's approximated IR spectra. So we used the information that we found from the DIBs and created a program where we could compare the absorptions that we were observing from space to the information in the RASCAL database. And this was done with the hopes to get some rough estimates of which molecules might be involved in creating these absorptions.
Using this RASCAL database.
Yeah. So from RASCAL, we got an idea of some potential candidate molecules which may be tied to these DIBs that we were looking into.
Ailish has confirmed, I think, what was suggested, that these two Hager DIBs have different sources.
Yeah, so that was going to be my next point. Yeah,
I
so
apologize.
No, that's great. That was a great time to come in. Yeah, so you can see that if you looked at the molecules from 5780 and the results that we got for 5797, the family of molecules which emerged are very different from each other. So again, confirming that they are likely two different molecular sources causing each of those DIB families.
Even though we are not 100% sure, nowhere
Right.
even near
Yes.
that these are the actual molecule, but at least you are pointing at the functional groups that are
Right.
common in these molecules that could be giving rise to these lines.
Right, yeah. It provides a way forward to keep our investigation going. So, of course, it's likely not one of these exact molecules, but it's pointing us in the right direction in terms of which functional groups may be present and which types of molecules to explore.
During your answer earlier on, Ailish, you mentioned other members of the group, including other students, colleagues of yours. So who are the members of the team that is working on this?
Okay, so I will just talk about a couple of the people. So the first of all, we have Professor Lou Massa, who is from City University in New York. He is an eminent quantum crystallographer, and in fact was the person who first mentioned this problem to us and suggested that we work on it. And that was 6 years ago, I think, and we've taken him up on his challenge ever since, and he has remained very involved in the project that he essentially began in 2019. And one of the other faculty members is Dr. Dan Majes, who is a graduate of St. Mary's University here in Halifax. He is a former Mount professor, currently an adjunct professor at the Mount, as he's now teaching in a US university. And his primary research is working on the cosmological distance scale, which determines things like expansion of the universe. But he's a very smart man and is essential to our team here. Dr. Circes Moreira-Boada is a theoretical chemist specializing in quantum chemistry and computational spectroscopy. She's working in Mexico currently, but is originally from Cuba. She's the most recent member of the faculty to join our team, but already she has made a significant contribution, and we are just delighted to have her working with us. That's mainly the faculty, and I will let Ailish talk about the students.
Yeah, so one of the first students highlighted here is Alice Surratt. So she joined our team as a visiting PhD student from Mexico. And she came and joined us in
And she's originally from?
And she's originally from Cuba.
Cuba, yeah.
Yeah, so she joined the team through the fall semester and a bit of the winter last year and helped us work on this problem and is, of course, still heavily involved in the research that is happening currently, though she has since returned back to Mexico. And the next students we have highlighted are Fraser and Emily Smith. So if I understand correctly, Fraser Smith would have been the first student to take on the DIB project, followed the next summer by his sister Emily. So they were both very interested in mathematics and both very intelligent siblings who both decided to come study at Mount Saint Vincent, who have now since both moved on to a master's program at St. Mary's University, though they also still stay involved with the work. We keep them all in the loop. And we have another student, Helena Zhang, who is studying in her undergraduate degree currently at Mount Saint Vincent University, has come onto the project and is still finishing off her degree currently.
Very good, very nice. So in closing this topic, I have been thinking a little bit about the type of problem that you're studying, which is an extremely difficult type of problem. And there is a reason for that philosophically, because when, in general, the easier type of problems are those where you have the cause and effect in that order. Here you have the effect, and you're trying to work your way backwards to get the cause that is causing that effect. In other words, it's called, in philosophy of science, I think it's called ill-posed problems, or at least an inverse problem. And there is a very nice book here by Charles Gruitch, Inverse Problems, which has a lot of examples worked out here, and it really is a very valuable addition to a library. And essentially there is a famous or an eminent mathematician by the name of Julia Robinson, who, by the way, won the Emmy Noether Award in mathematics. In the words of Julia Robinson, I read here, in the back cover of the book, it says, usually in mathematics, you have an equation and you want to find the solution. Here, you're given a solution and you had to find the equation. I like that. Mm-hmm. That's her word. Inverse problems are among the most difficult type of problems to solve. Can you please comment a bit on that?
Okay, I think the simplest way to talk about this is to give some examples, I think, that everyone would sort of understand. So can you imagine, for example, that you have a shadow on this table, and it's maybe the shape of an ellipse, and I say to you, what caused that shadow? Now, that is what we would call an ill-posed inverse problem, because in fact there is no unique answer. We could, for example, say that the shadow is caused by an elliptical plate directly above the shadow. But alternatively, we could say that it's caused by a ball at an acute angle causing the shadow. So that is a problem that has no solution. That is an inverse problem. The forward version of that problem would be to say, take the ball and ask somebody what the shadow looks like. That would be easy because you just shine the light on the ball. So that's one example. I have two other examples that I think will be familiar to people. On the left here are skid marks, and CSI technicians use skid marks to reconstruct accident scenes. So there is the observation or the effect being the skid marks, and they determine what the cause was. You know, was it the driver speeding or some other cause for the accident? On the right is a picture of a CT scanner. And CT scanners use the patterns formed by X-rays passing through the human body to reconstruct the position and shape of tumors. So again, it's an inverse problem because you've got the X-ray pattern and you have to reconstruct the cause of that, which, you know, is the tumor. So what we are studying with the DIBs is also an inverse problem, and I'm going to let Ailish talk about our specific inverse problem with the DIBs.
Yes, so as Tina mentioned, essentially an inverse problem is when you have the effect and you're working backwards to find the cause. And that's exactly what we're doing when we're investigating which molecules DIBs are coming from. So you can look at the absorption spectrum here. You'll see that we have all these absorptions that we can see, but we don't know exactly which molecule they're coming from. And again, that is our specific inverse problem. So we're taking these absorptions and we are essentially working backwards to see what exactly caused them. And one way to make sure you do this is essentially by eliminating the chance of coincidences as you work. So making sure at each step of your diagnostic process that you are exploring all possible options and making sure you can rule out any chance of coincidence or error.
Excellent. So in closing, was just wondering, do you have other interests? I'm sure you do. And artistic, musical, poetic, maybe Tina and maybe Ailish can start, and maybe, you know.
Yeah, I definitely have lots of hobbies and interests that I partake in outside of the scientific world. A big one for me is definitely music, so I do really enjoy listening to and playing music.
Do you play? What do you play?
So I won't say I play anything super well, but I'll say I'll pick up any instrument and give it a try. But I guess I do play guitar, and right now I'm picking up drumming, so that's
Good
what I'm
for you.
working on. Yep.
And I think you published a book with your mother or something.
Yes,
right?
so my next interest I was going to say is I do love spending time outdoors. So definitely hiking and kayaking or skiing, all things outdoors. And my mother and I have published a series of beach adventure books, so originating on Cape Breton Island, but now has spread over across Nova Scotia. So we do have a series of beach adventure journals.
Wow, how about Tina? I know every time I call you, you're on the plane somewhere, flying somewhere. So maybe.
Well, I have an eclectic mix of interests, just as my professional work is an eclectic mix. So I enjoy a number of outdoor activities as well, sort of biking and skiing and gardening, and I do yoga. But when I literally really want to get away from it all, I do take a flight.
Because you own a plane, you and your husband.
I do. I'm very fortunate to have a very small plane. But,
and you fly every week or something, or every couple of weeks?
We do. You have to keep it up to keep current, keep safe.
Yeah. So is there any question I should have asked you and I haven't asked so far?
Okay, well, I thought of one question which I think you could have asked us. How on earth do we think that we're going to solve a problem that nobody has been able to solve for 100 years? You know, are we arrogant? Hopefully not. And I think the reason why we feel we have a good chance of maybe making some progress, if not finding an answer, is that more than even 10 years ago, we have so much data available to us. There are telescopes in orbit producing vast amounts of data that is freely available for us to use, more so than any other people have had in the past. And that combined with the fact that we now have amazingly fast computers, powerful computers, one of which we have right here at the Mount, thanks, I think, to the CFI. Canada Foundation for Innovation. Right.
Yeah.
So I think those two things together make it much more realistic that we may make even baby steps towards finding a solution.
And the answer will be always tentative in this field, right?
Exactly.
It can never be 100% solid, closed answer, right? Because of the nature of the problem that is an inverse problem.
The number of DIBs and the even larger number of molecules that potentially exist, right? Yeah.
About Ailish, is there a question I should have asked, perhaps?
I guess you could have asked why I got involved with this project.
Okay, can you answer it?
Yeah, no, so I just thought that the work that you both were doing was really interesting, and more importantly, I wanted to get involved with research, of course, too, but it was a very welcoming group to join, and I think that was a big aspect of me getting involved in research and sticking with the research throughout my undergrad as heavily as I did was the support that was gained from all members of the research group, for sure. And of course, the interest in the topic.
We were very fortunate to have you.
Yes, I was going to say, we certainly were fortunate that you decided to work with us.
Yeah. Well, in the end, I thank you both very much, Professor Tina Harriott and Ailish Sullivan, two really great scientists, and thank you for the audience for your attention, and see you next time, and good night.